India is on its way back to the moon.
The historic mission to the moon and the launch of India's Chandrayaan 3 spacecraft.
India is literally shooting for the moon.
Chandrayaan 3 mission aims to touch down on the moon's largely unexplored South Pole.
Hello friends. On October 22, 2008, India successfully launched the Chandrayaan 1 mission, marking a significant achievement. This spacecraft accomplished a remarkable feat by reaching the moon and making a discovery of global significance: the presence of water. The revelation of water on the moon, a groundbreaking headline, was facilitated by Chandrayaan 1, providing compelling evidence that had never been obtained before. More specifically, this water was found in the South Pole region of the lunar surface. This groundbreaking revelation sparked a renewed interest in lunar exploration across nations worldwide. Consequently, nations like the USA and China have been consistently launching missions to explore the moon, eager to uncover its mysteries. However, all eyes are currently focused on India's Chandrayaan 3 mission, eagerly awaiting the new discoveries it might bring to light. The financial allocation for this project amounts to a total of $75 million. Furthermore, questions about the Chandrayaan 2 mission's failure have captured international attention. In the quest for answers, this video delves into the details of what went wrong with Chandrayaan 2 and explores the potential reasons behind its setbacks. As we unravel the mysteries of the moon and its exploration, Chandrayaan 3's upcoming mission holds the promise of unveiling even more remarkable insights. Missions directed towards the moon encompass a range of distinct categories, typically numbering between 5 to 6. These lunar missions initiated during the 1950s with advancements in human space exploration. As technology evolved over time, the intricacy of these endeavors also grew. The foremost and simplest class of these missions is the flyby mission. Within this mission type, a spacecraft is dispatched into space and traverses past the moon. Unlike orbiting the moon, the craft merely conducts a brief passage before continuing its trajectory. The Soviet Union achieved the inaugural successful flyby mission in January 1959 with Luna 1. Subsequently, in March 1959, the United States accomplished its first prosperous flyby mission with Pioneer 4, focused on remote lunar study. This early phase of flyby missions primarily aimed to examine the moon from a distance. During October 1959, the Soviet Union's Luna 3 mission proved pivotal as it furnished the world's initial close-up image of the moon's far side, which we cannot see from the Earth. While contemporary flyby missions predominantly transpire in conjunction with other space endeavors, when exclusive moon exploration is the objective, the subsequent category of missions, the orbiters, is deployed. Orbiter missions necessitate spacecraft to approach the moon and enter lunar orbit. This entails close proximity to the moon's surface and atmosphere examination. To date, over 40 triumphant orbiter missions have been accomplished, constituting the prevailing form of lunar exploration. The Soviet Union's Luna 10 mission of 1966 was the first thriving instance of an orbiter mission. Progressing from the orbiter category, the impact missions emerge. These missions extend the principles of orbiter missions. The primary spacecraft continues lunar orbit, while a distinct component separates and conducts a controlled crash landing onto the moon. The term impact missions arises from the collision occurring during the landing. This method serves a distinct purpose. The interval leading up to the crash landing offers opportunities for instrument readings. The readings gathered during this period significantly contribute to scientific understanding. An illustrative example of an impact mission is India's Chandrayaan 1. This mission included the Moon Impact Probe, which detached from the spacecraft and crash-landed on the moon. MIP housed Chandra's Altitudinal Composition Explorer, a mass spectrometer that continuously collected data as it approached the moon's surface. CHASE revealed the presence of water vapor in the lunar atmosphere. The impact was targeted at the Shackleton crater, with a point of contact named Jauhar Point. Chandrayaan 1 also featured an independent orbiter, housing NASA's Moon Mineralogy Mapper, which analyzed the lunar soil lifted by the impact. The fourth classification within the realm of moon missions involves lander missions. Here, a specific module of the spacecraft is dispatched to the moon with the intent of achieving a gentle, controlled landing rather than a crash impact. This intricate task necessitates a soft and precise landing, as the designated spacecraft component, commonly referred to as a lander, must touch down on the lunar surface without causing damage. This process is remarkably intricate and demanding. Initial attempts by both the US and the Soviet Union faced significant challenges, resulting in failures during the first 15 endeavors. In 1966, the Soviet Union achieved the pioneering successful landing on the moon through their Lunar 9 mission, signifying the world's maiden accomplishment of such a feat. This successful landing also yielded the first photographic glimpse of the lunar surface, albeit in a quality reflective of the technology available in 1966. In the past, a mere fraction of space missions achieved success. Similarly, only a small percentage of those who watch my videos are actually subscribed. So, if you end up liking this video, consider subscribing. It's free and you can always change your mind. Let's enhance this percentage just as the recent trend has seen a rise in the success rate of space missions. Now, let's dive into the video. Lander missions typically involve substantial and weighty modules, which, once landed, remain stationary and do not possess the capability to explore further. To address the need for mobility on the moon's surface, the subsequent rover missions emerged. Rovers are diminutive robotic vehicles outfitted with wheels that enable them to traverse the lunar terrain beyond the confines of the lander. This capability facilitates direct interaction with the lunar surface. The inception of rovers commenced with the Soviet Union successfully deploying the initial rover to the moon in November 1970. The concluding category within moon missions is human missions, which involve sending astronauts to the moon. These astronauts utilize landers for soft landings, disembarking to tread the lunar surface. Notably, this achievement was pioneered by the United States in 1969 when Neil Armstrong became the first human to set foot on the moon during NASA's Apollo 11 mission. The last human mission to the moon was conducted by NASA in 1972. Since then, no human has revisited the moon, and a total of only 12 individuals have experienced walking on its surface, all of whom were NASA astronauts. The intriguing question may arise regarding the sequence of rover missions following the initial human mission. This order is attributed to the fact that the primary goal of a human mission was a soft landing, whereas rover missions necessitated the development of new technologies for the construction of rovers. Subsequently, this technology was developed and realized in rover missions, emerging approximately a year after Neil Armstrong's historic moonwalk. In the context of the Chandrayaan 2 mission, it was conceived as a rover mission. The mission's intent was for the Vikram lander to softly descend and carry the rover, named Pragyan, which would then explore the lunar surface. Regrettably, this mission did not proceed as planned. On September 6, 2019, the Vikram lander of Chandrayaan 2, during its descent for a gentle landing, encountered an abrupt crash landing. Based on the findings presented in the November 2019 Failure Committee report, the incident's root cause was attributed to a software glitch. However, ISRO chose not to release this report to the public, a departure from its usual transparency. Prior to this incident, ISRO had maintained an open communication policy, sharing successes, failures, and explanations with the public. This incident marked a shift from this approach, which resulted in criticism towards ISRO. For several months, ISRO maintained that the lander remained intact and had not suffered damage, emphasizing that it was merely resting tilted on the lunar surface. Yet, under growing pressure, on January 1, 2020, ISRO's head acknowledged the unfortunate reality: the lander had indeed crashed and was irreparably damaged. Analysis of data from ISRO's Mission Control Center indicated that during Vikram lander's descent, it veered off course when it was approximately 2 kilometers above the surface. Subsequently, at an altitude of roughly 335 meters, contact with the lander was lost. The descent plan aimed for Vikram to significantly reduce its velocity by the time it reached 400 meters above the surface. However, even at a height of 1 kilometer, Vikram maintained a vertical velocity of 212 kilometers per hour and a horizontal velocity of 173 kilometers per hour. S. Somanath, ISRO's current chief, identified the issue as originating from Vikram's engine system. A slight variance in thrust among the 5 engines led to instability, preventing Vikram from achieving the necessary stability to capture landing site images. Attempts to correct the lander's trajectory triggered a spin due to thruster misalignment. Software constraints also limited the speed at which Vikram could rotate. These accumulated problems culminated in Vikram's eventual crash landing. Turning to Chandrayaan-3, it was launched with the objective of rectifying the deficiencies that prevented Chandrayaan-2's success. A series of modifications were introduced to minimize potential errors. Number 1, Chandrayaan-3 features an enlarged landing zone. While Chandrayaan-2 was confined to a 500 by 500 meter square area, Chandrayaan-3 enjoys a landing space spanning 4 by 2.4 kilometer square area, nearly 40 times larger than before. Number 2, the Vikram lander in Chandrayaan-3 is equipped with greater fuel capacity to extend its operational time above the lunar surface. This extension aims to afford the lander more time to identify a suitable landing location. Number 3, software upgrades enable Vikram to engage higher rotational speeds if necessary, addressing the previous issues with stability. And number 4, Chandrayaan-3's approach is not solely reliant on capturing images for landing. Alternate mechanisms are incorporated to enhance precision during landing. The Chandrayaan-2 mission has been deemed partially successful, with a notable accomplishment being the operational status of the orbiter launched as part of Chandrayaan-2. This orbiter continues to perform its functions while orbiting the Moon. The Chandrayaan-2 orbiter has captured high-resolution images, which have been utilized to aid the upcoming Vikram lander of Chandrayaan-3 in selecting accurate landing sites. Although the design of the Vikram lander in Chandrayaan-3 is largely similar to that of Chandrayaan-2, a few modifications have been introduced. These enhancements involve reinforcing the lander's legs, incorporating additional solar cells, and improving the sensors. The overarching mission objective of Chandrayaan-3 remains unchanged, focusing on landing at the Moon's south pole and deploying a rover. The chosen landing site resides at a latitude of 70 degrees south, encompassing numerous craters that remain perpetually in shadow, devoid of sunlight. The absence of sunlight suggests the potential presence of ice within these shaded craters. It's noteworthy that once the Chandrayaan-3 rover is placed on the lunar surface, it will have a single lunar day, equivalent to about 1 Earth month, to carry out its scientific experiments. This lunar day encompasses approximately 2 weeks of sunlight followed by 2 weeks of darkness. Thus, the ideal landing window for Chandrayaan-3 was expected to fall around August 23rd and 24th, allowing the rover a 14-day span to gather data. This scheduling is crucial because the instruments aboard Chandrayaan-3 are not engineered to endure the extreme cold temperatures that prevail during lunar nights, which can plummet to -232 degrees Celsius. Therefore, ISRO aims for a landing time aligned with the lunar sunrise, providing the rover with a functional period. Fortunately, Chandrayaan-3 has landed as expected. Delving into the technical specifics, the Vikram lander weighs 1,750 kilograms, while the rover, named Pragyan, weighs 26 kilograms. Chandrayaan-3 comprises 3 modules: the lander module, the rover module, and the propulsion module. The lander and rover modules possess defined roles, while the propulsion module is tasked with navigating Chandrayaan out of Earth's orbit and steering it towards the Moon. Once they reach a radius of 100 kilometers from the lunar surface, they will be separated from the propulsion module for the landing maneuver. Remarkably, Chandrayaan-3 does not include an orbiter module due to the continued functionality of Chandrayaan-2's orbiter, which will be repurposed. The propulsion module, however, will continue orbiting the Moon for an extended period of 3 to 6 months, serving communication purposes and conducting additional data collection activities. A device named Spectropolarimetry of Habitable Planet Earth is installed on the propulsion module, abbreviated as SHAPE. This instrument will scour space for small exoplanets. Moving on to the instruments aboard the Vikram lander and Pragyan rover, they are indeed intriguing. Pragyan houses 2 instruments: LIBS, Laser-Induced Breakdown Spectroscope, and APXS, Alpha Particle X-ray Spectrometer. LIBS will analyze the chemical composition of lunar soil, discerning the minerals present. Meanwhile, APXS will perform a similar analysis on lunar rocks. As Pragyan executes these tasks, the Vikram lander will capture corresponding images. The Vikram lander itself incorporates 4 instruments. RUMBA stands for Radio Anatomy of Moonbound Hypersensitive Ionosphere and Atmosphere. It aims to melt small moon rocks using a laser beam and analyze the resulting gas emissions. CHASTE, full form, is Chandra's Surface Thermophysical Experiment. Its role involves measuring thermal properties, including the temperature at the moon's south pole. ILSA, the Instrument for Lunar Seismic Activity, will gauge the frequency of seismic events, termed moonquakes, assisting in comprehending the moon's crust and mantle structure. LRA, Laser Retroreflector Array, provided by NASA. This instrument utilizes lasers to bounce signals from Earth, enabling precise calculations of Vikram lander's landing site and lunar distance. There are already 5 retroreflectors on the moon, enhancing the accuracy of distance measurements. In total, Chandrayaan-3 accommodates 7 instruments, often referred to as payloads. Beyond scientific pursuits, this mission carries a substantial element of national pride. A successful mission would establish India as the 4th nation, following the Soviet Union, the United States, and China, to achieve a soft moon landing. This achievement was originally poised for 2019 before Chandrayaan-2 encountered setbacks. In any case, the Chandrayaan-1 impact mission had already positioned India as the 5th country to reach the lunar surface, subsequent to the Soviet Union, the United States, Japan, and Europe. Over time, 4 more countries, China, Israel, Luxembourg, and the United Arab Emirates, have joined this exclusive club, achieving moon landings between 2009 and 2022. Following Chandrayaan-3, India's next prominent endeavor is the Gaganyaan mission. This initiative involves crafting a spacecraft capable of transporting Indian astronauts into orbit. Initially slated for 2022, the mission has encountered delays and is now expected to be realized in 2025. In the broader context of moon missions, Russia's recent Luna 25 launch was followed by news of its crash on the lunar surface, signifying mission failure. On a different trajectory, America's Artemis II is planned for November 2024, involving human orbit around the moon. This endeavor will mark the furthest human space travel to date. Similarly, China is gearing up to dispatch astronauts to the moon in the years ahead. If you have found this video informative, I hope you will also like my other space-related videos. Thank you sincerely for your support. We will meet again very soon, but in the meantime, please feel free to explore my other videos. Goodbye.